If you're bored, you can simply close your eyes and rotate a cow in your mind. It's free, and the cops can't stop you.
Hey everybody, alright, Cody here, and we're going to talk about some rasterization. So rasterization is a good way to draw a cow from 3D space onto a 2D computer screen, and it uses a fair amount of calculus. So I'm going to try to keep it quick because I've only got about, 5 or so minutes, and last time I did this it was 15 minutes, so let's go quick. Alright, what is rasterization? Rasterization is when you have a point in 3D space and you have a bunch of points in 3D space, and you project it onto a 2D plane in order to form an image. So here we have, let me select this layer. Here we have an eye, very cute eye, and here we have a box in space, very cool. And here we have a plane, and this is a plane in 3D space, very nice. So we are going to draw a line from each of these corners of the box to the eye. And we'll do that with yellow. So we're going to go from this upper left corner to the eye, and this upper right corner to the eye, and this bottom right corner to the eye, and this other bottom left corner to the eye. Very cool. And what we're going to see is that if we track the point where each of those vectors from the corners of the box to the eye intersect with our plane, we're going to see an image is formed upon that screen. So we'll go like so. Oh, give me a layer I can draw on. Here, and then here, and then here, and then here. Isn't that neat? So a box is projected onto this 2D plane. So how do we do it? Let's go. All right. It starts with the vector equation of a line. So we should be familiar with vectors. They were one of the first things we did in Calc 3. Given a point, P, which is usually the starting point, and vector PQ, function of T gives us P plus T vector PQ. And the vector equation of a plane is the normal vector dotted with P naught, a point that is known to be on the plane, and P, any other point in the plane, equal to 0. So, and this is the thing that I think is really cool about this. We mush these equations together because if we know we've selected a point on the plane. How do we find the point where this line will be in the plane? We just plug this equation for the line in right here. And wherever we get here, that will give us T to tell us, hey, at T, this equation holds true. That's your point that's in the plane. So it'll make a little bit more sense as I go with some color. So let's combine these two equations. N is our normal vector to the plane. And real quick, how do we determine that? The normal vector to the plane is based off of the camera to the object. To the origin. So if you have your origin point as 0, 0, 0, and you have your eye over here, and the eye is looking at the origin, and we have a vector right here, this is the normal vector to the plane. The plane is projected off of that vector. So everything is based off of the eye to the 0, 0, 0 vector. The system would require a little bit of tweaking if the camera was allowed to look away from the origin. But for my mathematical purposes and lack of knowledge, it does not. So coming back over here, the normal vector to the plane, which we know is going to be our I to origin line. And that is going to be dot product with P from up here on our line equation. Let's get this to where we can see what's going on. There we go. It's going to be P, and then back over here. I'm sorry, P plus T. A little bit of an error there. And vector PQ. This is just the same as the line equation because we're literally plugging and chugging here. But then we have to put this part back in. So it's minus P naught, which is the point that we've selected on the plane, equals 0. And okay, cool. Now we have mushed our equation of the line into the equation of the plane. But now we got to solve for t, because that's what we're trying to find, is the point along the vector that is equal here. So we're going to do a little bit of kung fu here. We're going to say the normal dotted with, and here's an important point I want to point out. This is a point, the starting point of the line, and this is a point on the plane. And what do you get when you have a point minus a point? You get another vector. So over here we have the normal P minus P naught from our plane equation plus T times the normal vector. I'm sorry, dotting the normal vector with PQ. I should be clear. Equals 0. That's pretty sweet. So now we have gotten t kind of broken out of the middle of these parentheses, but t still needs to be isolated. At this point, it's just straight up algebra. So we're going to move this to the left side of the equation, and that's going to give us t normal vector dot PQ equals, my brain shut down for a second there, equals minus n dot P minus P0, P naught. And then now we need to isolate t further. We want t, so we are going to divide both sides by the normal dotted with our vector that I forgot to put the line on, PQ. So that's going to come over here, and it's going to be n over, n dotted with PQ vector. Sweet. And that ultimately gives us the equation that we need to solve for t. T equals minus normal vector dotted with P minus P naught. And this is P minus P naught over the normal plane dotted with PQ. Now, when it comes to, we can solve for this, and t will give us the point on the plane, the point on the line that is within the plane. And once we've solved for t, we can go right back up to our original vector equation of a line and plug in t, and that will give us our xy coordinates. So when it comes to computer speak, we're looking at it this way. N, we have said, is the camera to origin. Oh goodness, having trouble typing here. Cam to origin vector. So I'm just going to keep that as n because that's a lot to write there. N dotted with, and our first dot here is the camera to plane vector. So camera to plane, which for our purposes is the same as the camera to the origin, because the camera to origin is the same as the normal plane, over normal plane dotted with camera to target, which is one of the vertices on our 3D object. And that is rarely equivalent because if, for example, real quick, we had our eyeball and we had our origin, and this is our shape right here, and this is normal, then this point where it intersects should be, if this is along the X and Y, and then this direction is the Z axis, then this point should be 0, 0, and then some Z number. And that's how I've coded it in my program. Now, I do know that there are other right-hand or left-hand orientations where X is this way, and then Y is this way, and then Z is this way, and my brain doesn't work very well that way, so this is how I've coded it. But that is something to be aware of when you're working in 3D, because I ran across these issues as I proceeded to work on the program. So now I'll work out a quick example, and we will move on to the other short aspects that we do in our code here. All right, so we're going to work out a quick example problem. We have some predefined stuff here to save a little bit of time. I've got a camera point at 0 on the X, 0 on the Y, and then 1,000 points away from the origin. The origin's at 0, 0, 0, which makes sense. The camera to origin vector is 0, 0, negative 1,000, which makes sense. And then our plane normal, which is defined from our camera to origin, is 0, 0, 1. Because we technically is 0, 0, 1,000, but it's a unit vector. The problem works either way. And then we have a known point on the plane, which is calculated as some sort of a ratio. I usually would say if the camera is here and the point is here, then I want the view plane to be like 1/4 of the way. So plane known point 0, 0, 750. But that can be whatever. So the target we have said is at -15, 20, and 10. So now we're just going to plug it into our equation that we made earlier. We've got, I'm going to write it out so I don't make any errors. We've got negative of the, man, my zoom is being weird. We got negative of 0, 0, 1 for the normal vector, dotted with cam to plane, which is going to be 0, 0, 250, because that's just a 1,000 in the Z camera, minus 1,000, minus 750 from the camera, from the plane known point, which is just the center of the plane. And all that is going to be over the top of, once again, our normal vector, 0, 0, 1, dotted with our camera to target. And this is what's important to get right, because if this isn't right, then you're not pointing at the target. So if we're going to make a line here, because this hasn't been declared yet. If camera is at point 0, 0, 1,000, that's cam, and target, one of our pixels, or one of the vertices on our polygon, the pixel is going to be on the screen. We're solving for the pixel. And the target is at -15, 20, and 10. And I subtract target from camera to get a line. We're going to get +15, -20, and +990, which will go camera to plane. So it'll go 15 -20, 990. And now we're going to do dot product and solve this out. So we're going to scooch on over. I'm going to zoom in, scroll up. That's what I'll do. All right. So the top side is going to be, I'm going to switch colors so you can see what I'm talking about. It's going to be 0 times 0. So it's going to be 0. It's going to be 0 times 0, which is again going to be 0. And this is a -1 because this is the negative normal. So it's -1 times 250. So it's going to be -250. Nice. Easy. Because these all sum together for dot product. So top half is negative 250. Now the bottom half, we're going to go 0 times 15, which is 0. Once again, these normal vectors are nice. 0 times negative 20, which is once again 0. And then we have 1 times 990. So 990 will be right here. And we have t. We have now solved for t. So t equals minus 250 over 990. And now we plug that into our equation of the line. And what is the equation of the line? It is p of t is equal to the starting point, which for our camera is 0, 0, 1000, plus t, which is minus 250 over 990, of that is multiplied by our camera to target vector, which is here. So 15 minus 20, 990. So this is a scalar multiple, and this will just multiply against each one of these. So 15 times minus 250 divided by 990 is going to give us negative 3.787878, and so on and so forth. But we're working with pixels, so we're going to round to the nearest value, because you could go with the sub-pixel, but then I'd have to start dealing with shaders, and I'm not about that. So it is going to be rounded to 4. Get rid of that. 4. And then same thing for the y-axis. We're going to do negative 250 times negative 20, which is going to give us positive 5,000 divided by 990, and that is going to give us 5.05.05.5. And that's fine, because we're going to get around that to 5. And then for our z, it's going to be minus 250 times 990 divided by 990, so that's just going to be minus 250. Sweet, easy peasy. So I seem to have made a sign error. That 4 should be a negative 4. Because this should be not minus 250. This should be 750. Oh, no, we're good. That makes sense. Because this is being summed with the camera start point. So the camera is 0, 0, 1000, and being added to it is our multiplied t value right here, so it's going to be plus 4. Sorry, these should be in vector brackets so that we know that I'm not just a mad lad. 4, 5, minus 250. So you sum each of the corresponding components, and our resulting point is 4, 5, 750, which makes sense. So that's a good thing, because we know that the plane, oh, why did it rotate? We know that the plane is 750 pixels away. So if the intersection point was not 750 pixels away, we would know that some error had occurred. But that's good. That works out. So now we have found the point. When we start drawing to the screen, though, we don't really need 750. The only thing that matters for us is the x and y values, because a plane is one-dimensional. Two-dimensional, not three-dimensional. So we don't need a z value, and we already knew the z value anyways. So that's how you draw a single point on a screen that is the point of intersection between a line and a plane. So if you have a cow, and a cow is made of 1,000 triangles, and each of those triangles has 3 points, you only need to do this 3,000 times, and then you can draw a cow. Hey, and just one more time, I want to mention that was supposed to be negative 4, not a positive 4. I forgot to hold the sign when I rounded from negative 3 in the fraction. But anyways, yep, that's how you do it, and thanks for watching.